Remember, when we determine the number of steps required for an algorithm, we often use the worst-case scenario. But it's possible that our worst-case scenario never actually happens, so we might end up with a wild overestimate of the time complexity of the algorithm. To help avoid this problem, we introduce big O notation. We say that g of n is big O of f of n if there is some positive constant c where for all sufficiently large n, g of n is less than or equal to some multiple of f of n, in which case we write g of n is big O of f of n. For example, we want to show that g of n equals 1000n is big O of n squared. We want to show that if n is large enough, there's a constant c that will make 1000n less than or equal to cn squared. Now, since we want this, since n is assumed a positive integer, we can divide by it. And now, since the right-hand side is a product of two positive numbers, we can make it as large as we want, so there's no question of being able to satisfy the inequality. So if we choose c, we can then determine what n is large enough. So if c is equal to 1, then we find that n is greater than or equal to 1000. In other words, 1000n is less than or equal to n squared for n greater than or equal to 1000. And so that tells us that 1000n is big O of n squared. Generally speaking, we don't need to be this precise, and so we can take a general strategy. We'll find a g1n where, for sufficiently large n, g of n is less than or equal to g1n, and g1 of n is, in some sense, a simpler function. And then lather, rinse, repeat, until we can eventually get to a function that is a constant multiple of f of n. So again, let's take those two functions. And for n large enough, we know that n is less than or equal to n squared. And so 1000n is less than or equal to 1000n squared, which is 1000f of n. And so g of n is big O of f of n. Or we could take a more complicated polynomial. So if we want to maintain the inequality, the key is to replace something with something bigger. So 100n, well, if I multiply that by n again, I get something bigger. And 50,000, if I multiply that by n squared, I get something bigger. And so now I have a bunch of n squareds, and I can add them, and I can replace that coefficient with a bigger, easier number. And so our function is big O of n squared. Or we could take something like this, and we can do a little bit of algebra and split that up. But again, for sufficiently large n, the square root is less than or equal to n itself, and so I can replace that square root n with something bigger and maintain the inequality. And consequently, square root 1000n is less than or equal to 100n, and so it's big O of n. Now, g of n being big O of f of n means that for sufficiently large n, there's some constant that makes g of n less than or equal to c f of n. But what if no c makes this happen? We might consider if there's a c where, for sufficiently large n, g of n is always bigger than c times f of n. And this suggests the following. G of n is omega of f of n if there's some positive constant c where, for all sufficiently large n, g of n is greater than or equal to c times f of n, in which case we write g of n is omega of f of n. So let's show that n squared is omega of 1000n. So the idea here is we want to replace n squared with something that will be smaller for sufficiently large n. And in this case, we note that if n is greater than or equal to 1000, then n squared is greater than or equal to 1000n, which is 1 times 1000n, and so n squared is omega of 1000n. And again, we can employ the same strategy by constantly replacing the function with something simpler. For example, something like this. Now, since we're comparing our function to n squared, let's try to set up a sequence of inequalities that replace all non-quadratic terms. So if n is greater than or equal to, how about 1,000, then n cubed is greater than or equal to 1,000 n squared, so we can replace n cubed with something smaller. Now, since we're subtracting 1,000 n, we can subtract even more and maintain the inequality. Since we're assuming n is greater than or equal to 1,000, then n squared is greater than or equal to 1,000 n. So if we subtract n squared instead of 1,000 n, we get something even smaller. And so we're greater than or equal to 998 n squared. And so we have a constant, 998, where for all sufficiently large n, namely n greater than or equal to 1,000, our function is greater than 998 n squared. And so our function is omega of n squared. If g of n is big O of f of n, then there's some positive constant c where g of n is less than or equal to cf of n for all sufficiently large n. And if gn is omega of f of n, then there's some positive c prime where gn is greater for all sufficiently large n. So if g of n is in both, then g of n is sandwiched between constant multiples of f of n. And so in some sense, g of n is close to f of n. And this motivates the following definition for theta of f of n, which will be the intersection of big O of f of n with omega of f of n. And we say that g is order of f of n. What this means is that if g of n is order f of n, then we have lower and upper bounds on the values of g of n for sufficiently large n. This means if g of n is the time complexity of an algorithm, we have upper and lower bounds on how long it will take to finish running the algorithm. While this would be a good thing to know, remember, no one ever complained when a job was completed ahead of schedule. This means that in practice, we're more worried about the upper bound, so we generally care about finding f of n where g of n is big O of f of n. We'll take a look at how to do that next.